Welcome to lesson 12 on power system analysis. In this lesson, we will discuss modeling of transformers. Well, this lesson we will start with introduction of transformers, then concept of an ideal transformer, then we will go into physical transformers and their equivalent circuit. After that, we will talk about three-phase transformers and three-winding transformers. Well, the main objective of this lesson is to explain the concept of an ideal transformer. That is, once you are through this lesson, then you should be able to explain the concept of ideal transformer, develop the equation or the equivalent circuits models for single phase transformers, then three-phase transformers and three-winding transformers. Well, we all know that transformers are an integral part of any electrical network. As you can see from this diagram, that we have generation from generators which is normally in the voltage range of 11 to 30 kV, and then we connect it to a transmission network which may be working at levels of 400, 220 or 132 kV, and then again this goes into substations from where we distribute power at lower voltages, maybe at 33 kV, 11 kV or 3-phase 400 volts. So, at all these at different levels we see we need different voltage levels, and for changing these voltage levels we require these transformers. Therefore, transformers are an integral part of any power system network, and we have very large number of transformers in any electrical network. Therefore, it is necessary for us for doing a proper analysis to make a good model of the transformer in our analysis. Now, what are transformers? Transformers are basically a static electrical machine which has a magnetic core on which windings are placed. Now, this magnetic core provides the path for the fluxes. As you can see in this diagram, we have a magnetic core, a rectangular magnetic core which has two windows cut in it, and we have placed the windings on the central limb of this core. Now, this whenever we energize this winding with an alternating voltage, we are going to set up an alternating current in these windings which will produce the flux, which is an alternating flux, and this core provides a path for the alternating flux. Therefore, the core has to be of the a magnetic material. Normally, we use steel, and especially the steel which we call cold rolled grain oriented silicon steel, because it provides lesser losses. Now, this type of a transformer which we have shown here, where we have put the windings on the central limb and we have the flux paths from both sides, this type of a transformer we call a shell type transformer. Another type of transformer which we call core type transformer will have the windings on the two extreme limbs, and the flux path is provided by this core as shown here. Now, how does this transformer work? Before we model the transformer, we must know how it is working, and therefore, we will see how it is going to work. Now, as if we see this transformer, we have two windings placed on the two limbs of this transformer. Now, once we energize one of the winding, say this winding 1 with a voltage V1, what happens is as current will start flowing in this winding. This current will also be an alternating current, and this will set up an alternating flux in the core. Now, this flux, since it is alternating or time varying, is going to cut this winding also. So, number of turns of this winding, and this is going to therefore produce a voltage. As per Lenge's law, the voltage which is induced by these flux cutting of these flux lines will be opposing this voltage V1. So, we will get a voltage E1 here, which will be very nearly equal to V1, and the flux which is set up here is also going to cut the number of turns of the winding on this other limb, and therefore, it is going to set up a voltage E2 on this winding also, that is across this winding also, and therefore, a voltage V2 at the two terminals of this winding. This is how the transformer operates, but in order to get into details of this, what we will do is we will first try to understand the operation of this transformer, assuming it to be an ideal machine, and later we will see how we can model the physical transformer which is not really an ideal one. So, first we will get into a concept of ideal transformer. Now, what is an ideal transformer? It is basically a transformer where we make certain assumptions. This we say as the transformer core has infinite permeability. What do we mean by this? We basically mean that 0 mmf is required to create magnetic flux in the core. That is, it is a negligible current which will set up the magnetic flux in the core, or almost a 0 current which is going to set up a magnetic flux in the core, which simply means that the core reluctance is 0, its permeability is infinite. Another aspect of this is that infinite permeability is that all the flux will be confined to the core itself. There will not be any flux which will be flowing through the outside air, because the reluctance offered by the core is 0, and the reluctance offered by outside air is going to be much higher as compared to this. Therefore, all the flux will be confined to the core itself. We make another assumption that transformer winding has 0 resistance. This basically means that there is no power loss in the winding, that is, I square R losses taking place in the winding is neglected. We also mean by this that there is going to be no ohmic voltage drop, that is, IR drop in the winding is also 0. There is going to be no voltage drop in the winding because of the current flowing through it. We make another assumption that transformer core has 0 core loss. Now, what does this mean? Because we know that if we have alternating flux set up in any magnetic material, we are going to have losses, magnetic losses, which will be in terms of hysteresis loss and eddy current loss. For an ideal transformer, we assume that these losses are 0. Okay, so with these assumptions, we get into an ideal transformer and to understand the basic operation of a transformer. So, let us see, if we see this diagram, we have a core which we assume to have infinite permeability, on which we have a winding on one limb and a winding on the other limb. Now, these windings are assumed to have 0 resistance, and we also assume that the core has no losses. Now, generally the two windings are termed as primary winding, on which side we put the source, and the other winding where we are going to put the load is called a secondary winding. Though in a network where power can flow in reverse direction also, the concept of primary and secondary winding does not really work. What we need to use in that case is high voltage winding and low voltage winding. So, because you are going to have one side at a high voltage, another side at a low voltage. So, that is the term which is more appropriate to use. Though for our analysis here, we can term them as this side, that is side 1, as a primary, where we are injecting a source voltage, and the other side we can call them as secondary. They can be, this side can be a low voltage side, this side can be a high voltage side. Then we call this transformer as a step up transformer. If this side is at higher voltage than this side, then we call it as a low voltage, a step down transformer. Okay, so now we see how does this transformer work. So we have connected a alternating voltage source with a voltage V1 to this primary side or side 1 winding. What is going to happen is, as we said earlier, almost with negligible amount of current flowing through this winding, we will have a flux setup, flux phi setup in the core. This flux will be an alternating flux, and this will be cutting the turns of this winding, which will induce a voltage E1 in this winding. This E1, as per Lenge's law, will be opposing this voltage V1. So, the polarities will be as marked here, that is, this will be positive, this will be negative. And so, now what will be the magnitude of this E1, or what will be this voltage, induced voltage E1? V1 is the applied voltage, which will be equal to E1, because we have assumed there is no losses or no voltage drop which is taking place. Therefore, V1 is equal to E1, and what will be the value of E1? E1 will be equal to d lambda by dt, that is the flux linkage, the derivative of flux linkage with time, which we can write as N1 into d phi by dt. So, we have E1 equal to N1 into d phi by dt. Now, this flux phi, which is a time varying flux, is also linking this coil. We have assumed 0 permeability. So, all the flux is confined to this core. Therefore, all the flux set up by this winding is also linking this winding. Therefore, we have a voltage induced across this winding, which will be equal to E2, and this E2 will be equal to N2 into d phi by dt, again the rate of change of flux which is cutting this winding. So, where N2 is the number of turns of this winding. So, and since there is no voltage drop, so across the terminals of this winding we will get voltage V2, which will be equal to E2. Now, looking at these two relationships, we can write that V1 by V2 is equal to E1 by E2, which will be equal to N1 by N2, which we call equal to A, where A is called the turns ratio between the primary and the secondary turns of the winding of a transformer. This is a very important relationship. Here we have used capital V1, V2 and E1, E2 to indicate that if we are using sinusoidal voltage sources, then these are our phasors. So, the phasor relationship will also be similar, that is V1 by V2 is equal to N1 by N2 is equal to A, the turns ratio of the transformer. Now, the instantaneous voltage V1, if we are using a sinusoidal voltage source, can be written as equal to root 2 times V1, where V1 is the magnitude of the peak value, magnitude of the phasor, and sin omega t. And d phi by dt, since we have seen that V1 is equal to N1 d phi by dt. Therefore, we can write d phi by dt is equal to V1 by N1, where V1 is given by this relationship. So, we get d phi by dt is equal to root 2 by N1 into V1 sin omega t. Integrating this, we will get phi is equal to root 2 by omega N1 into V1 cos omega t, which we can also write as root 2 by omega N1 into V1 sin omega t minus pi by 2. What does this equation tell us? This tells us that the flux which is produced by this voltage that we have applied is going to lag the voltage by 90 degrees, because here we see it is sin omega t minus phi by 2. So, flux is lagging the voltage which is creating this flux in the core by 90 degrees. So, flux lags the voltage by 90 degree. Also, the current which flows in the winding to create this flux is going to be in phase with the flux. Therefore, the current will also be lagging the voltage by 90 degree. Now, what is the maximum value of the flux in the core? This will be equal to root 2 by omega N1 into V1, because when sin omega t minus pi by 2 is equal to 1, that will give me the maximum value of the flux. So, phi max is equal to root 2 by omega N1 into V1. From this, we can write V1 by N1, which is nothing but voltage per unit or per turn for the winding. So, dividing V1 by N1 means each turn is having how much voltage across it, or is inducing or how much voltage across it. So, V1 by N1 is equal to omega into phi max by root 2. From here, from this equation, we can write that V1 by N1 is equal to omega goes on this side and root 2 comes below. So, omega phi max by root 2, this is equal to twice pi f by root 2 into phi max can be written as A into B max, where A is the area of the cross section of the core. So, we have omega is equal to twice pi f. So, V1 by N1 is equal to twice pi f by root 2 into A into B max, which is equal to 4.44 f A B max, which tells us that the voltage induced per turn on any transformer is proportional to frequency, the area of cross section, and the maximum flux density allowed in the core material. This is a very important relationship for designing a transformer, because this is going to tell what should be the volume of the core material. Now, we will see if we connect a load on the second winding or the secondary winding of the transformer, what is going to happen. We had seen that if we had applied this alternating voltage here, we had an induced voltage E1, which was very nearly equal to or equal to V1 coming across this winding 1, and a voltage E2 was induced across the winding 2, which was equal to V2, the terminal voltage across the winding. Now, if we connect a load here across these two terminals, what will happen? Since there is a voltage V2 here, there is going to be a current I2 flowing into the load, where I2 will be equal to V2 by Z. The Z is the impedance of the load. So, we are going to get this current I2. Now, what is going to happen because of this current I2? This current I2, when it flows through this winding, is going to produce a flux, which will again be an alternating flux, which will be, as we see from the right hand rule, this flux will be opposing the flux set up by the first winding. That is, if we see this thing as the current direction with our fingers, and the thumb direction will give us the flux direction phi. So, if we see this direction of the flux due to the current flowing in winding 2 will be opposing the flux set up by the first winding. Now, as we have seen, the voltage induced here is equal to N1 into d phi by dt. Now, if the flux produced by this winding is opposing the flux produced by this, the resultant flux in the core is going to reduce. If this resultant flux reduces, the voltage here is also going to reduce, because it is equal to N into d phi, where phi is the resultant flux in the core. Now, that cannot happen because this E1 will be equal to V1, because we have assumed no voltage drop here. So, this voltage must be equal to this V1, which can come only if we have the same amount of flux in the core. For neutralizing the opposing flux produced by the secondary winding, what will happen is we will have a reflected current I1 flowing in the first winding, which will produce an MMF equal to I1 N1, which will be exactly neutralizing the flux produced by the MMF I2 N2. Therefore, under conditions of load put on the secondary side, we have I1 N1 minus I2 N2. This will be equal to R into phi, where we have assumed reluctance to be 0. So, this is 0, which means I1 N1 must be equal to I2 N2. That is, if a current starts flowing in the secondary winding, there is going to be a current which will flow in primary winding and which will produce a MMF which will be exactly equal and opposite to the MMF produced by the current flowing in the secondary winding. So, whenever a current flows in the secondary winding, we have a current also flowing in the primary winding, producing an MMF I1 N1, which will be exactly equal to the MMF produced by the current flowing in the secondary winding, that is I2 N2. Therefore, from this relationship we get I1 by I2 is equal to N2 by N1, which is equal to V2 by V1, and which is equal to 1 by A, where A is the turns ratio of the transformer. A is equal to N1 by N2. So, this is how an ideal transformer works in case when it is loaded. Another important aspect of a transformer is that it does not only transform the voltage or the current levels and the two sides of the transformer, it also provides a transformer of or transformation of the impedance level on the two sides of the transformer. Now, we can see this from this diagram, that if we have a voltage V1 applied across this winding 1, and we have a voltage V2 across this terminal of the winding 2, and we have put a load Z across this second winding terminals, then we have a current I2 equal to V2 by Z flowing in this second winding. Now, when this is flowing in this winding, we will have a current I1 flowing in the primary winding, producing I1 N1 equal to I2 N2. Therefore, we have I1 is equal to N2 by N1 into I2, and if we look at this side, we have Z2 is equal to V2 by I2. Now, we can write this as, since we know V2 V1 by V2 is equal to N1 by N2, or V2 by V1 is equal to N2 by N1. Therefore, we can write V2 is equal to N2 by N1 into V1, and for I2 we can write that I2 is equal to N1 by N2 into I1. Therefore, we can write that Z2 dash, which is the impedance as seen from this side. Impedance seen from this side will be equal to how much? V1 by I1. So, Z2 dash is equal to V1 by I1, and this will be equal to how much? If we see this V1 by I1 on this side, then this goes in the numerator and this term goes in the denominator. If we do that, then this we find that this is equal to N1 by N2 square into Z2. That is, if Z2 is the impedance connected on the secondary side, then this impedance is seen by the primary side as equal to N1 by N2 square into Z2. That is, it is equal to A square Z2, where A is the turns ratio. So, if A is more than 1, that is, it is a step down transformer, then we will find that the impedance, a small impedance on this side, can be seen as a large impedance on this side. Sometimes this is used for impedance matching in many circuits. So, impedance transformation is another aspect which is used in these transformers. Now, we have seen that V1 by V2 is equal to N1 by N2, and I1 by I2 is equal to N2 by N1. And if we see in these transformers, we have assumed no losses in the core as well as no losses in the winding. So, the power on the two sides have to be equal, because there is no power which is lost in the windings or in the core. Now, the power, instantaneous power P1 on the primary side will be equal to V1 I1, instantaneous power P2 on the secondary side will be equal to V2 into I2. Since these two power must be equal, as there is no losses, so V1 I1 must be equal to V2 I2. If we write in terms of phasors for a sinusoidal voltage sources, then we have V1 I1 conjugate is equal to V2 I2 conjugate, where V1 I1 conjugate is called the complex power P plus jQ, and V2 I2 conjugate is the complex power on the secondary side. So, we have the complex powers on the two sides equal to each other. So, this is what we have learnt about the ideal transformer operation. Of course, the transformers that we use in our system are certainly not ideal transformers. They are made up of components which are physically available, and these components do not have these ideal characteristics. Therefore, we will try to model the transformers, a physical transformer, by trying to introduce these physical characteristics of these transformers or transformer material. Now, first we will take that we know that the iron core that we use does not have infinite permeability, but it has finite permeability. What does it mean? It means that to set up any flux in the core, we require certain amount of current, that is I1 N1 will be required, or an MMF will be required to set up a flux in the core, because the core has finite amount of reluctance, that is MMF is equal to reluctance into flux, and since reluctance is not 0, therefore, to set up the flux we need a finite amount of I1 N1, that is a finite amount of current is required to flow in the winding to set up the flux. Then we also know that whenever there is an alternating flux in the core, we are going to have losses in the core in terms of hysteresis and eddy current losses. We will take care of those also. No winding is having material which has no resistance, that is all winding material, mostly we use copper, and for that has certain amount of resistance. Therefore, there is going to be losses in the winding. Because of this resistance also there is going to be a voltage drop in the winding. Then we will also take care of, since we have seen that the core material is not infinite, therefore, the whole flux phi may not be confined to this core itself. There may be some amount of core which will a certain amount of core may be flowing across this path, that is, it will not link both the windings. And that kind of flux we call as the leakage flux. Therefore, we will take care of the leakage flux also. So, we will build the model for a physical transformer. Now, first we will take the effect of finite permeability. What does it say? It says that since the permeability is finite, which means we need a certain amount of MMF to produce the flux. Now, we have seen that the current which produces the flux is going to be at 90 degrees to the voltage which is applied, because the flux lags the voltage by 90 degree, and therefore, the current which is producing this flux, since it will be in phase with the flux, will also lag the voltage by 90 degrees. Now, how do we represent this current which is required to produce the flux? We need this current to lag the applied voltage by 90 degree, and we know the electrical parameter which provides this kind of a relationship is an inductance. Therefore, we provide an inductor here with a reactance Xm to represent the finite permeability or the magnetizing part of the current to flow in the circuit. So, if we have a voltage V1 applied and we have a reactance Xm representing this magnetization or the finite permeability, then we will have a current I1m flowing through this, and this I1m will be lagging the voltage by 90 degrees, and this is what we want for to represent the magnetizing part of the transformer. So, I1m will lag this voltage V1, and this will be represented by a reactance Xm. Now, since this I1m flows here, so the current which will flow here will be I1 minus I1m, or I1, the current flowing, will be equal to I2 dash plus I1m, where I2 dash will be equal to I2 by A on this side. If I2 is flowing on the secondary side, then on the primary side the reflected current will be I2 by A, which we write as I2 dash. So, I1 will be equal to I1m plus I2 dash in this case. Now, what will be the value of I1m? I1m will be equal to, since we know that the flux is going to be produced by the MMF I1m into N1, and this m into N1 is equal to reluctance of the core material into phi. Therefore, we can write I1m is equal to R into phi divided by N1, which is equal to R by N1 into phi will be, as we have seen earlier, can be represented by root 2 V1 by omega N1 sin omega t minus pi by 2. Therefore, the magnitude value of I1m will be equal to R into V1 by omega N1 square, and since we know that this current is going to lag the voltage by 90 degree, we can write the phasor as I1m is equal to R by V1 into j omega N1 square, where this 1 by j is indicating a lag of 90 degrees, which is equal to V1 by jxm. That is what we will see here. The I1m is equal to V1 by jxm. So, xm therefore can be defined as omega N1 square by reluctance R. This we can also write as 1 by Bm, where B is the susceptance and X is the reactance. Now, when the transformer is not loaded, then we have I1 is equal to I1m. This is equal to V1 by jxm, and since there is no current which is flowing in the secondary side, and we have assumed no losses in the system, P1 will be equal to 0, and Q1, which is the reactive power, will be equal to V1 square by xm. Now, we will take care of the core losses. Now, we say that core losses have two parts, one is hysteresis, another is eddy current. So, we can take care of both these losses by providing an element of resistance RC. So, if we put a resistance RC in parallel with this XM, that will provide us the model for core losses, because here what will happen is V1 by RC will provide a current flowing through this, which is we call as IC. This IC into IC square into RC will be equal to the core losses of the transformer. Now, why we put this in parallel here, that is, or across voltage V1, is that once we energize this transformer, a flux is set up and core losses are going to be present, whether we have any load on the transformer or not. So, even for unloaded transformer, since a flux is set up, this alternating flux is going to create losses, and therefore, these losses have to be taken care of. So, as soon as you apply a voltage here, you will have a current flowing through this, and therefore, I square RC losses will be coming. Also, now we will take care of the effect of winding loss and leakage flux. Now, for winding losses, since we know that each winding is made up of copper or aluminum which has finite resistance, so the winding resistance can be used to represent the losses in the winding. Like on the primary side of the winding, we have the resistance of the winding as RS1. This will be put here to represent the losses in the primary winding. Similarly, on the secondary side, the winding will have resistance RS2, and so this RS2 represents the losses on the secondary side winding. Now, as we said, certain amount of flux may not be linking both the windings. These flux we call as the leakage flux, that is, some flux produced by winding 1 may not be linking the second winding, because the flux path can be through the air also. It may not be, all the flux may not be confined to the core. Therefore, in that case that part of the flux will not be linking the other winding, and this flux we call as the leakage flux. And the leakage flux can be represented by means of reactance. So, XS1 here, the reactance is representing the leakage flux of primary winding. Similarly, the current flowing on the secondary side due to the load will also produce a flux, and all this flux may not link the primary side of the winding, that is, some will leak through the air path, and therefore, this is represented by XS2 here. These will be in series with the resistance of the winding, because these are going to be proportional to the current flowing in the winding. So, we have So, we have the complete transformer model here, where we have represented the finite permeability by this Bm, the core losses by this Gc. Gc is the conductance, which is 1 by R. So, 1 by Rc is this Gc. Since these two arms are in parallel, it will be easier to work with admittances, that is conductance and susceptance, rather than resistance and reactance. Therefore, most of the time we write them in terms of conductance and susceptance. Conductance Gc representing the core loss part, susceptance Bm representing the magnetizing current part. Rs represents the resistance of the primary winding, XS1 represents the leakage reactance of the primary winding, XS2 the leakage reactance of the secondary winding, Rs2 is the resistance of the secondary winding. And we can generally combine this two as impedance Zs1 of the primary winding and impedance Zs2 of the secondary winding, where Zs1 is equal to Rs1 plus Jxs1 and Zs2 is Rs2 plus Jsx2. The current here on the primary side at the terminal will be I1. The current in this winding will be I1 minus I1m, and which will be equal to I2 dash, and that will be equal to I2 by A. So, I2 by A current will flow in this winding, and I2 current will flow in this winding depending on the load on the secondary side of the transformer. Now, as we have seen earlier, we can transform the impedance from one side to the other side. Therefore, what secondary side impedance, what we have done is transformed them on the primary side or brought them to the primary side, or we are looking at all the impedance from the primary side. In that case, the secondary side impedances XS2 becomes A square XS2 and Rs2 becomes A square Rs2 on the primary side. So, this is now complete circuit of equivalent circuit of a transformer with an ideal transformer placed here. Now, there is another aspect which we can use to further simplify this circuit. Now, we know this current I1m will be lagging the voltage applied by 90 degrees. Therefore, we almost by 90 degrees, because this current, the losses in the core is not very large. So, this current being 90 degree, this current being in phase with V1, the actual current will be lagging the voltage by an angle which will be less than 90 degree, but very near to 90 degrees. So, we are representing this current like this, and since this current I1 is going to depend on the load current, the loads will have a power factor very nearly equal to 8.85, 0.9 or so. So, this current I2 dash here, which is a reflected current for I2, will be very nearly in phase with voltage V1, and therefore, the current I1 is going to be the phasor sum of this I2 dash and I1m is also going to be very much nearly equal to I2 dash here, because this is very small. The losses or the magnetizing current for a transformer or an unloaded transformer takes only about 3 to 5% of the full load current. So, this is almost 1 by 30 or 1 by 20 of this. Therefore, we find this I1 will be very nearly equal to I2 and very much in phase with I2 dash. Therefore, what we can do is we can shift this from here to this side itself, because I1 and I2 dash are very nearly equal. Then our equivalent circuit becomes like this, because we can now combine RS1 and RS2 and XS1 and XS2. So, we can write them as RS plus j XS, where RS is equal to RS1 plus RS2 and XS is equal to XS1 plus XS2. So, this is now the equivalent circuit, which represents the magnetization current, the core losses, the winding losses and the leakage flux. So, this is an equivalent circuit for a physical transformer. So, as we said, the impedance, winding and the leakage part is taken care of by Zs. Zs is equal to Rs plus jXs, and Ym is the admittance of the parallel path, which is equal to Gc or 1 by Rm plus 1 by Jxm. Rs is equal to Rs1 plus a square Rs2, and Xs is equal to Xs1 plus a square Xs2. And for any physical transformer, the value of Rs is very, very small compared to Rm, because core losses are very small. So, they are represented by a very large resistance, because the current flowing through them is very small. It is V1 by Rm, and this current is very small. So, Rm will be much larger than Rs. Similarly, Xs is much smaller than Xm, and also Xs is much greater than Rs for any physical transformer. Now, we will go into three-phase transformers. Now, three-phase transformers are basically built up by connecting three single-phase transformers, or we can have three sets of windings on the same core or a single core with 5 limbs or 3 limbs. So, we can build three-phase transformers. Now, three-phase transformers have another characteristics, because we have 3 windings, we can connect them in star or in delta. So, we have different combinations of windings. The primary side can be star, secondary side can also be star. The primary side can be delta, secondary side can be star. The primary side can be star, secondary side can be delta, and so on. So, we have various combinations which are available. Now, here we have shown how 3 windings can be connected to create a star-star transformer, which will look like this. Now, here the high voltage windings we are representing by H. So, H1, H2, H3 represents the 3 terminals of the high voltage winding, to which phase A, B and C are connected. Similarly, X1, X2, X3 represent the 3 terminals of the low voltage winding, to which A, B and C phase are connected. The small case letters indicate low voltage, the bold case letters indicate the high voltage. This is a star-star transformer which can be created like this. Now, since the equivalent circuit of single phase transformer and 3-phase transformers will be exactly same, as 3-phase transformers are built using 3 single phase transformers, or you use with a core with 3 limbs on which the 3-phase windings are placed. So, here again also you have core losses, you have finite permeability, you have winding resistance, and leakage flux. So, they can be represented in the same way. So, the transformer, 3-phase transformer are very similar or almost same as equivalent circuit go. So, except for one difference that we find, and that difference is if we have a star delta transformer, then if you will see the phase voltages of these, for say this transformer, the phase voltage A is in this direction, whereas the phase voltage A will be in this direction as indicated here. So, VA is in this direction and VA, capital A, that is high voltage side voltage, is in this direction as shown here. There is going to be a difference of 30 degree in the phase angle whenever we have a star delta transformer. This needs to be taken care of in the equivalent circuit. This we do by using the same kind of an equivalent circuit that we have built earlier, where we have the admittance Ym in parallel, which is indicating the core losses and the magnetization current, and impedance Zs in series, which is representing the resistance and the leakage flux of the windings, the ideal transformer, and we have a phase shifting introduced. This phase shifting will be plus or minus 30 degree depending on which side is delta and which side is star. So, the equivalent circuit of a 3-phase transformer is very similar to that single phase transformer. In fact, for all analysis of 3-phase transformers, what we do is generally we work with a single phase or a phasor values of voltage and current, because we most of the time work with balanced circuits, and therefore, each of the 3 phases will have the same voltages and current, except that they will be 120 degree out of phase from each other. There is another kind of transformer which we use in power systems, which we call 3-winding transformers. Now, instead of the 2 windings that we have seen, a primary and a secondary winding, or a high voltage low voltage winding on a normal transformer, these transformers have 3 windings. This is generally used in certain places where we need 2 different voltage levels or 3 different voltage levels. Say you have a power coming from say in a power station, you have the generator voltage at say 20 kV, and you are connecting it to the transmission side. So, you have say a 400 kV transmission line, then the voltage on the other side is 400 kV, and for the auxiliaries of the of the generators, we need, since you have feed water pumps, you have compressors, you have so many equipment in the power plant which require power supply, and this is provided by means of another winding which is at a much lower voltage of say 3.3 kV or 6.6 kV, which is used for supplying the power to the auxiliaries of the power plant. So, also many places we use devices which are used for reactive power compensation and other things. Now, these devices can also be connected at the much lower voltage, because the cost of devices at lower voltage is much lower than that at high voltages. So, many places we need another voltage level, there we use this 3-winding transformers. The 3rd winding is normally called a tertiary winding. There is another advantage with this 3-winding transformer, that is, if you have unbalanced loading, then if you have a star delta transformer, then in that case on the delta side the 0 sequence current can flow, because it will appear as a closed circuit for the 0 sequence current, which are basically 3rd harmonic currents. but if you have a star star transformer, then this 0 sequence currents cannot flow in that, and this creates a shifting of the neutral. So, many times to provide path for these 0 sequence currents in the transformer, we provide this tertiary winding, which is normally connected in delta, and this provides the path for that. Now, here we are showing these 3 windings. ZP is the primary, ZS is the tertiary, and ZT is the ZS is the secondary, and ZT is the tertiary winding. We can now find the values of these windings by conducting tests, say leakage impedance measured in primary with secondary short circuited and tertiary open. ZPT we can find out as leakage impedance measured in the primary with tertiary short circuited and secondary open. That is, you short circuit the tertiary, open the secondary winding, and provide a voltage source on the primary side. Whatever voltage divided by current you get will be the leakage impedance measured in primary with tertiary short circuited and secondary open. Similarly, if you leakage impedance measured in secondary with tertiary short circuited and primary open can give us ZST. Now, once we calculate this, we can find out the values of ZP, ZS and ZT as this. So, with this we have now been able to model the transformers, the single phase transformer, 3 phase transformers, and also 3 winding transformers. Now, what in a system we have, say, a generator, a transformer, transmission line, another transformer, a step up transformer here, a step down transformer here, then the total circuit will look like this. If we have a star delta transformer, then we have the phase shifting introduced here. Okay. So, this is the way we get the equivalent circuit for the system, and most of the time the resistance being very small and the core loss part and the magnetization current is very small. So, we represent the transformer by a simple reactance also. This is what is shown here. This is again another circuit with a load and a transformer. Again here we have introduced this phase shifter because this is a delta star transformer. So, this is all about transformer modeling. Thank you.